All right, we're recording. Awesome. So I was looking at chapter 4, and to be honest with you, I think really I'm going to spend the bulk of the time on chapters 6 and 7, because chapter 4 is just stoichiometry, and the beginning of it was what's a strong acid, what's a strong base, memorizing what those things are, and I think you guys have that down pretty cold. The other thing from chapter 4 was balancing oxidation and reduction reactions, which you know how to do quite well. And then it's stoichiometry, which you know how to do very well. So the only real thing is maybe a hydrate. Anybody, and again, don't use your names, but anybody remember what a hydrate is? Well, hydrate is water. You're right. A hydrate is a crystal that's got water in it. So if they write something like this, sodium chloride, big dot, 5 waters, this is a sodium chloride crystal with water trapped inside. So you've got your crystal, and if there's water trapped inside the crystal, we call it a hydrate. If there's no water trapped inside the crystal, like this one, there's no water in there, then we say it's anhydrous. And the number of waters trapped inside the crystal depend on the ionic compound. Salts, as you know, are anything that dissolve. Salts are ionic compounds. Salts are ionic compounds.
So the anhydrous is the crystal without water.
Without water, yep. So it'd just be pure sodium chloride.
How come it doesn't?
So most crystals do trap water in it.
No, I mean, how come it doesn't dissolve? Because it's a salt.
No, no, that's not what I said.
I don't know.
I said,
NaCl and water, how come it doesn't
oh,
dissolve?
this is, so if I have sodium chloride and I just sit it out, okay, there's humidity in the air.
Oh.
And so some of the water in the air goes into the crystal.
Oh.
But if I put sodium chloride into a beaker of water, it will dissolve.
Yeah.
Yeah, that's really, I don't really think there's anything else too earth-shattering here. So I'm going to move on to chapter 5. Because we reviewed balancing oxidation and reduction in chapter 17. Let's see. Well, let's just make sure you know the difference between ideal gas theory and real gas theory. So an ideal gas, we would say it's a point mass, which means it has mass but no volume. Whereas a real gas takes up space and volume. Another component of ideal gas theory is that ideal gases, they have elastic collisions, which means no energy is lost during the collision. So normally when two things collide, there's some sort of heat generated and you're going to lose some energy that way. So some of the, because you've got kinetic energy of this guy moving, kinetic energy of this guy moving, when they collide, the total energy should be the sum of the two, but when they collide, actually it's less because some of the energy is converted to heat. But for elastic collisions, we pretend that no energy is lost. And you guys can interrupt me too if you have a question, like what do I mean? And the third.
Mr. Larson, please call 4404. Mr. Larson, please call 4404.
Random motion. We assume that the gas particles are moving independently of each other. So then obviously with real gases, it's just the opposite. Collisions aren't elastic. Motion is not random. Because gas particles can attract each other if they get close enough. Or if it's a polar gas, like if you're talking about water vapor in the air, H2O is polar. So if you got two water molecules floating around in the air, if they get close enough, their dipoles are going to attract. The ideal gas equation, PV equals nRT, whereas the real gas equation is P plus A N over V squared, or we can just say N squared over V squared, times V minus NB equals nRT.
Is that A?
That's an A. Okay. So these two terms, A N squared over V squared and minus NB, due to the fact that we are taking into account these factors. So because gas particles actually take up size, take up space, from point number one, we have to subtract out the space that the gas particle occupies. So B is the size of the gas particle, and B is basically the number of moles. So the more gas particles you have, the more space they're going to take up. And then you multiply it by their size.
What is A?
I'll get to A. So if I was going to ask you which has got the largest size, which gas particle's got the largest size? Hydrogen, oxygen, or iodine. Well, let's not do iodine because sometimes it's liquid. So let's do chlorine. Which one's bigger? Chlorine. Chlorine's in the third energy level, much bigger than oxygen, but second bigger than hydrogen, that's in the first. So it's got the biggest B value. So which one is going to act the most non-ideal? In ideal, we pretend all gases are the same size. When it's real, then we take into account their size. So the one that's going to behave the least like an ideal gas is the one that's the biggest, so the chlorine. A has to do with the fact that the collisions aren't elastic and that the motion isn't random. And it has to do with how pressure is created. When a gas particle strikes the side of a container, that's how pressure is created. But if the gas particles are more attracted to each other, if they're attracted to each other, they're not going to hit the balloon or whatever the wall of your container with as much force. So that's going to affect the pressure. So A basically is for the attractiveness of the gas. How attracted are they to each other? and then the n squared over v squared, that has to do with the concentration.
Would you be able to predict A without looking it up?
You could predict a relative strength.
Like of the gas, like of the specific gases, is there a trend on the periodic table?
For the most part, yes. You know, you could predict it. Now, the way you actually get A is by doing it experimentally, finding the actual number. But relatively, you could predict pretty good.
What's the trend on the periodic table?
There is no trend on the periodic table.
Oh, okay.
The what it's based off of is really polar or non-polar and size of the molecule combined. N is the moles, V is the volume. So if you have lots of moles in a small volume, you can have a very dense concentration of gas, so there's going to be a greater attraction. If you have very few moles and a very big volume, well then the gas particles aren't going to be very close to one another, and therefore the attraction will be smaller. Now, as far as your question goes, predicting, suppose we had these gases, carbon dioxide gas, ammonia gas, and sure, why not? Water vapor. And no, let's leave water out. Let's just do CO2, NH3, and H2. So which gases are going to be most attracted to each other? Well, we know a little bit about that dipoles are going to be more attractive than nonpolars. So if I do the Lewis dot structure for carbon dioxide, this is what I get. This one is symmetrical. Carbon dioxide is nonpolar. So if another carbon dioxide molecule comes nearby, there's nothing really to attract these two together. Similarly, hydrogen. Hydrogen is nonpolar. So there's really nothing that's going to cause one hydrogen molecule to be attracted to another. But ammonia has a lone pair of electrons. And that lone pair of electrons is going to make this side partially negative and this side partially positive. So ammonia gas does have a reason to be attracted to another one. The partial positive on one side is going to be attracted to the partial negative. So the one that would have the greatest attractive forces is going to be the ammonia. It'd be dipole-dipole. Yeah. Because you have the partial negative on one attracted to the partial positive on the other. Now, if there is a little bit of an attractive force between one carbon dioxide molecule and the other. What is that force when it's two nonpolars? What attracts two nonpolars together? London dispersion or van der Waals. So you've got London dispersion or van der Waals. And essentially, all you're saying with these is that the electrons in one molecule are attracted to the protons in the other, okay? But because the electron density is, if I were to draw a cloud, the electron density is equally distributed. And because the electron density is equally distributed, one side of the molecule doesn't have a partial negative. But when you draw the electron density of, let's say, ammonia, the electron density cloud looks like that. One side of the molecule has a lot of negative charge due to the electrons. So the electron cloud in this one is attracted to the protons in the other molecule. And because it's symmetrical, there is not much of an attraction. Now, if I were to compare carbon dioxide to hydrogen, hydrogen is a very small molecule. Its electron density is equally distributed. The bigger your molecule you have, the greater the likelihood two molecules will bump into each other. And even though this is nonpolar, the bigger your molecule, the greater the attraction, okay? So CO2 has very little attraction, but it will have more attraction than the hydrogen. So this would be 2, and this would be 3.
So London dispersion is just the electrons and protons just aligning. Kind of.
Not, I wouldn't say aligning,
Well,
but,
not, but
they-
just like
they attract
finding
to each other. Yeah.
Okay.
but because there's no like unequalness in the distribution, there's not a great attraction.
Okay. And like, yeah, there's some forces like pushing against because of like the like charges, right?
Like if I drew methanoic acid, it looks a little bit similar to this. You have a carbon in the center, 2 oxygens coming off, but this molecule is no longer symmetrical. On this side of the molecule, there's a lot of electron density. This side, not so much. So now this side has got a lot of electron density, it's a partial negative. So when you have symmetrical molecules, there's no separation of charge, so they don't attract. One last thing I was just going to mention, just as a reminder, if you have a very large nonpolar molecule, it is possible, like if you take butane is a gas, but pentane is a liquid. And the reason why that is that because pentane is so big, and these are all hydrogens on the end that I didn't draw in, because pentane is so big, in fact I'll remove them now, there's enough van der Waals forces between the 2 pentanes to bring them together to form a liquid. Okay. It's not like they have to be lined up or anything. But this is van der Waals forces, and there's enough force there to bring them together to form a liquid. So even if you're nonpolar, if you're big enough, you can be brought together to form a liquid, and if you're really super long, you can be brought together to form a solid.
How long does it have to be a solid?
I don't know.
It's graphite, yeah.
Graphite is a network covalent, so it's a little bit different because in graphite, there's not a molecule of graphite, it's just this repeating hexon. My guess is you gotta get into like hundreds of carbons long before it would. And also too, it kind of forms a weird state when they're that thick, that When do you gotta use the real gas equation? As opposed to the ideal? Under what conditions? So very low volumes and very high pressures. You have to use the real gas equation. But most of the time, if you're dealing at normal pressures and normal volumes, the ideal gas equation will give you the exact same answer as the real one.
What's considered like a very low, and like
Well, it depends partly on which gas you're dealing with, but I mean, you're talking, I don't know, really small. Okay, this would be a good thing to review. Kinetic energy. The average kinetic energy is 3/2 RT. Kinetic energy is 1/2 mv squared. And if you're dealing with the average kinetic energy, it would be the average of your velocities. So that's average kinetic energy.
Is this still chapter 4?
No, this is chapter 5, sorry.
what's the second equation?
This is the equation for kinetic energy. And so when you look at this equation, kinetic energy is
Oh,
related to
yeah,
3/2 RT. R is the universal gas constant, 8.31. T is temperature in Kelvin. So this doesn't hurt to remind you. If your gases are all at the same temperature, what did I do wrong?
I'm just confused, like, are those two
The same
equations are the
thing.
same?
No,
What's this difference between the second?
I'm just telling you what kinetic energy is.
Yeah, so one
Kinetic
is
energy
like,
is 1/2 mv squared.
But
So
like,
technically
the
that's
first
equal to 3/2 RT.
So this is equal to 3/2 RT.
Okay.
I just didn't write it, I didn't put that there because we typically don't use this to calculate the temperature. What they're gonna do is they're gonna give you a graph, and they're gonna give you a graph, let's say, something like this. You could do, we did number of molecules, or moles, and then did kinetic energy. And I drew this is, let's say, oxygen, and then I drew this one to be, let's make them all the same. Drew this one to be nitrogen, and I drew one more to be hydrogen. But then I asked you which one of those is got the greatest temperature, or are they all at the same temperature? So which one has the greatest temperature, or are they all at the same?
Of two.
So this is where, like, we kind of look at the equation. What's the average kinetic energy? The one with the greatest average kinetic energy is going to have the greatest temperature, okay? Because temperature is just a measurement of how fast the particles are moving in the air. If the particles are moving really fast, you have a big temperature. If the particles are moving slow, you have a low temperature. So the average is the P. So here's my average for the oxygen, here's my average for the nitrogen, here's my average for the hydrogen. So which one's got the highest average kinetic energy? The hydrogen. So who's gonna have the greatest temperature? The hydrogen. Okay. So they're not gonna ask you to manipulate this equation. They're gonna ask you something like I just said, who's got the highest temperature? And then the corollary to that one is the one like this, where they go oops. Which one's got the greatest temperature? Well, they're all at the same temperature. They all are got the same average. So if they say something like, 3 gases are at 25 degrees Celsius, which one has the greatest kinetic energy? If you're at the same temperature, you all have the same kinetic energy, okay? So, once again, if you're all at the same temperature, you have the same average kinetic energy. Something else we talked about in chapter 5 is the root mean squared. The root mean squared is exactly what it says it is. It's the root of the mean of the square. And we use u, remember u and v are the same thing, velocity. So the root of the mean of the square. And in this case, u is the speed of the gas particles in your sample. So the average squared speed. And that is more predictive of how fast a gas will move or diffuse. So if I have a tube, and my tube is distance d, and I release my gas particles, and I want to find out how long is it going to take for my gas to diffuse all the way across to the other side. I don't use my velocity, because like if you were like driving a car, cars go in straight lines. So if I was driving a car, I said, well, how long is it going to take me to go from here to here? I use my velocity, because cars go in straight lines, hopefully. But gas particles don't do that. They go boom, 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 boom. So it's going to take a while for all these gas particles colliding to work their way all the way down the tube. And it is more predictive to use that, the root mean squared, to predict how long it would take. I wouldn't use v, I would use the root mean squared. The root mean squared is equal to the square root of 3RTM. I won't go through the mathematics of it because we did that back when we did chapter 5. But basically, if you take the kinetic energy, you can set it to 3/2 RT, you can get this. M is the molar mass. So basically, you're saying the root mean squared, or how fast something is going to diffuse, is going to depend on its mass. How big is it? How heavy is it? And it's going to depend on its temperature. Because if it's got a big temperature, it's going to bounce around that tube and get to the other end a lot quicker. If it's got a low temperature, it's going to bounce around slower. Graham's law is where, yep.
Does M have to be in kilograms?
Ooh, good point. Yes, the molar mass must be in kilograms. And that, yes, good call. In kilograms, the molar mass in kilograms. Because otherwise it won't cancel with the units in R. Yep.
So for R, do you use 8.31 or do you use
8.31 for R. Almost always do you use 8.31 except for one, like, I'm trying to remember what chapter that was, we had to use .0821.
Is
We use
that,
.08.
So liters times average over moles times gallon.
You can use 8.31 for the ideal gas law. It was,
So
I thought it was the equilibrium constant. When calculating KP, I think we have to use 0.0821.
Is the 8.31, is that in kilopascals?
and joules.
8.31 is
Joules per mole Kelvin.
liters kPa per mole Kelvin. But this is equal to 8.31 joules per mole
Oh,
Kelvin. Because a liter times a kPa is a joule. Oh, sorry.
Yeah.
So Graham's law is when we say the root mean squared for gas 1, because that's the root mean squared. So the root mean squared of gas 1 over the root mean squared of gas 2 is equal to the molar mass of gas 2 over the molar mass of gas 1. So one thing they would like to do to you is do something like the diffusion rate of gas B is twice as big as gas A. What can we say about their relative masses? So, if gas B diffuses as twice the greater rate of gas A, so if I square this, I'm just making gas B gas 2 because I wanted it down there. So if I square this, so what can we say about their relative masses then? Who's bigger, gas A or gas B? Who's heavier? I mean, who's got the bigger mass?
B.
Well, think about this. They're at the same temperature. Gas B diffused faster.
Okay.
So A is going to be bigger because a lighter gas is going to move quicker through the tube. A heavier gas is going to move slower if they're at the same temperature, and they are. But how much bigger is gas A? Well, 4 times as big, 4 times the mass, because it gets squared. So lighter gases diffuse faster than heavier gases, as long as they're at the same temperature.
Where's B and where's A?
Ice made gas B number 2 and gas A number 1. So, so if it's diffusing twice as big, its speed is going to be twice as big as A.
Okay.
What if I said it's 3 times as much? How much bigger is A now? 9. So not, gas A is 9 times as heavy as gas B. Why don't we try number 2 in that little packet that I handed out to you. This is from 2003. So you've got a rigid 5-liter cylinder that contains nitrogen and oxygen gas. Calculate the total pressure of nitrogen and oxygen, okay? So we've got a cylinder, it's rigid, so it's not gonna change shape. It's got nitrogen and oxygen. Are these two gases reacting? Is there any reaction going on in here? Okay, good. Because if there's a reaction going on, then we approach the problem differently. But these two gases are acting independently of each other, they're not doing anything. So the total pressure in here should be the sum of the individual pressures. We've got 24.5 grams of nitrogen and 28 grams of oxygen. So 24.5 grams of nitrogen and that's going to give me 28 grams of nitrogen is 1 mole, and I've got 28 grams of oxygen and 32 grams of oxygen gives me 1 mole of oxygen.
It's 0.875 moles of nitrogen.
Thank you.
And 0.875 moles of oxygen.
The same?
Mm-hmm.
Okay, so you can probably tell that's by design. The number of moles are equal, so that means the pressure exerted by the nitrogen is equal to the pressure exerted by the oxygen, because they have the same number of moles. They don't give us the total pressure. We can calculate the pressure using PV equals nRT. Now you wouldn't do this separately for each of these, because that would take, well actually we could just do it for one of them because the pressure will be the same, because of the ideal gas equation. So P is equal to nRT over V. The pressure is going to be 0.875 moles times, do they want it in a certain pressure? ATMs, so we'll use the 0.0821 times our temperature, which is 298, over our volume, 5 liters. And I get 4.28 atmospheres. So if one of these is 4.28 atmospheres, then because their moles are equal, the other one will be as well, and the total pressure will be 8.56 ATMs. Okay, it says for B, the temperature is decreased. Can I erase this? So right now, what is the ratio of nitrogen to oxygen in our container? 50-50, right? They have the same number of moles. This is at 298. If I decrease, Calvin, if I decrease the temperature, will that affect the amount of nitrogen and oxygen in there? No. So the ratio will still stay the same. Now, remember I said there's no reaction going on. It'd be a whole other story if there was some reaction, like if they had, I don't know, hydrogen gas and oxygen gas in there, and they're looking at some sort of equilibrium reaction. They're not. The nitrogen and the oxygen, the ratio will stay the same. If you lower the temperature, it just means they can be moving slower, okay? So if they're moving slower, they will hit the container with less force, your pressure will be less. So all you gotta do is recalculate PV equals nRT, but this time, instead of using 298, you're gonna use 280. And that will give you the total pressure. And I'll just do that real quick. At 4.02. So instead of being 4.28, the pressure dropped to 4.02. And it would be the same for the oxygen. Okay, if the cylinder develops a pin-size hole leak, some of the gas escapes. Would the ratio of N2 and O2 increase, decrease, or remain the same? Now it gets interesting. So there's a hole in the bucket, dear Liza. You decrease the temperature, the ratio stayed the same. But now, are the two gas molecules going to diffuse at the same rate? Or is one going to move faster than the other one out the hole? Now, what did we just get done talking about when we had Graham's law up here? Who diffuses faster, a heavier gas or a lighter gas?
Lighter.
The lighter gas. So which one's lighter, nitrogen or oxygen?
Nitrogen.
Nitrogen. So the nitrogen gas will leave the container at a faster rate than the oxygen. So that means if the nitrogen's leaving at a faster rate, the partial pressure of nitrogen will go down at a faster rate. So, did they ask us to calculate it or just?
No,
No.
Okay, so it's going to the ratio of the moles. Well, the ratio of moles of N2 over O2, the ratio will get smaller, right? Because, and this is where you gotta be careful, if the number on top gets smaller, that means the ratio is getting smaller. Okay? Oh, now they're doing a reaction. A different rigid container contains 0.176 moles of nitrogen monoxide. A 0.176 sample of oxygen is added to the cylinder where a reaction occurs to produce NO2. So we've got nitrogen monoxide, 0.176 moles of it, and we're going to add an equal amount of oxygen. And so the nitrogen monoxide and the oxygen are going to react to produce nitrogen dioxide. To balance it off, we're going to need 2 there and 2 there, and were balanced, right? So calculate the total pressure after the reaction is complete. So they do not give us a KP. So we have to assume that the reaction goes to completion. Just making sure I'm not missing anything here. Okay, so I don't see it, if they gave us a KP, okay, if they gave us a KP, we'd have to do an ice table and do our concentrations and shift and find the equilibrium concentrations based off of we'd have to do that if they gave us a K value for this reaction. They did not give us a K value. So if there's no K value, then we're assuming that the reaction is going to completion, and therefore it's just a limiting reactant problem, meaning which one are we going to run out of first? Are we going to run out of nitrogen monoxide first or oxygen first? Which will be the limiting reactant? Well, we can kind of already tell. They gave us the same number of moles. The nitrogen monoxide will be used up as twice as fast as the oxygen, right? So before my reaction, I have this many moles of each. These will be used up faster. So after the reaction is done, all of it is gone. How much oxygen will be left? Half as much. How much of the nitrogen dioxide will be produced? 0.176 moles, because the amount of this should be equal to the amount of that when we're all done. If you don't believe me, work out the stoichiometry, which you can always do. 176 moles, 2 moles of NO will give me 2 moles of NO2. So So that's the number of moles of those gases when we're done. Now calculate the total pressure. They didn't ask for the partial pressure, so all of this guy is gone. See you later, alligator. Some of the oxygen disappeared, and the nitrogen dioxide appeared. You probably can't tell the color difference. But there's more NO2 now than there is oxygen. There, now I feel better. But they want the total pressure. And when you're doing with the total pressure, we don't care if it's oxygen or nitrogen, we can just add the two together. If we add the two together, I get 0.264. Now, if you want, you can take this and plug it into PV equals nRT to find the total pressure. Because you got the total moles, you got R, you got T, you got P, you got V. The container's 5 liters. Now, when we did this in the beginning, these were the number of moles we had, right? Part 1. And we calculated the total pressure to be, each one was what, 4.28? Right? If I add up the moles, that would be 3.52. So what happened to our total number of moles? It decreased, right? Now they gave us some nice numbers. How much did our total number of moles decrease by? Decreased by, should be decreased by 3/2. No, it decreased by 3/4. It's gotta get smaller. The mole's gotta get smaller.
Oh yeah.
So if you take this number,
No, yeah.
if you take this number and you multiply it by 3/4, if you multiply it by 3/4, that's the number you get. So the moles decreased by 3/4. Sorry to my viewing friends in Poland, I screwed up. It's not 3/2, it's 3/4. So, yak shamash. So 3/4.
Is that kind of a mistake then?
That counts as a mistake.
Alright, fantastic.
Actually, I should say shaprash. So 3/4 of my moles gives me that. So if my moles decreases by 3/4, my pressure is going to decrease by 3/4. So it'd be quicker to say, okay, here's my pressure, here's my pressure. The total pressure originally was 8.56. That's the original total pressure. If my moles decrease by 3/4, my pressure is going to decrease by 3/4.
So but you could just plug it back in.
But you could just take the total moles and just plug it in PV equals nRT. I'm just saying,
Yeah.
I'm just showing you a quicker way to do it, especially if you're given a problem like this on the multiple choice where there's no calculator involved.
Yeah.
You could say to yourself, oh, I'm decreasing the moles by 1/2, the pressure's going to decrease by 1/2.
Wait,
So-
sorry.
No, it's okay.
Wait, but I thought it was a different equation now, or a different like situation. So why can we use the part from part A,
It's like a different container.
the different stuff? Like it's not N2 and O2, it's.
No, well, it says a different rigid container,
But it's different. It's also.
but
it's
the
not,
conditions are the same,
But
so.
it's not N2 and O2, which is what it was originally. Now it's NO and O2.
Oh, well, yeah, but the only thing that changes is
And the actual.
Well, but then the ratio's different too.
yeah, but no.
So, okay, I see what you're saying.
Yeah.
In the original problem, it was N2,
Yeah.
but the moles were the same,
Right.
right? So, that's one of, again, the beauties of the ideal gas equation.
All gases are the same.
All gases are treated the same, so as long as it's 0.76 moles, I don't care what the gas is, it's gonna have that pressure. So whatever the gas is, if you've got 0.176 moles of it, the pressure's gonna be 4.28. So I was using the knowledge of that to say, oh, okay, well, in the second part, in part E, I've got this many moles of NO. So if I have that many moles of NO, well then that's gonna be my pressure, and the ratio will be the same, it'll just be a different gas. Instead of being 50-50 nitrogen and oxygen, it's gonna be 50-50 nitrogen monoxide and oxygen.
But does it matter that the mole ratio changed?
The mole ratio,
Of like the NO and O2?
Cause NO is 2.
Cause it's like 2 moles of NO for every mole of oxygen.
yes, that's why the pressure decreased.
Yeah, but like, so that doesn't matter that the N to an O2 ratio was not the same. Does that make sense?
That still lets us use the
This,
original.
so
0.352
starting,
number.
the ratios were the same of NO
Yeah.
and O2.
But,
But
okay.
NO got used up at a faster rate, so at the end, the ratio is different.
So,
Okay.
but the 2 in front of the NO doesn't
It's
change.
you
It's
can
still
still
fine.
use the
Yeah, I was thinking
0.352
still
numbers, right?
But it just
You-
Doesn't
even-
stop
Oh.
the same number of moles.
They
Yeah,
told us
I
we had
thought
this
the
many
same thing you
moles,
were.
so it doesn't matter what that number is up there.
Okay.
That number is just used to find out who's the limiting reactant, okay? These are all very good questions, all very good questions. So, I think what we'll do then is, we'll end here, and then for the next review session, I'll pick up with chapter 6 and chapter 7.
What's the next review?
Next review section is next week, Thursday.
Do you have a game?
Yeah, we have
Ooh, next week Thursday.
What?
the next year.